Cool. Thank you, Zephyr, and thanks for the opportunity to present today. So I'm going to, for the next half hour, I'm going to be talking about Arm Automotive Solutions, which is our automotive reference stack. And I've subtitled the talk "Pushing the Limits of Yocto." I'm going to attempt to justify that slightly lofty title in the next 30 minutes. So first of all, about me. I'm a staff software engineer in the automotive software team at Arm. I won't go through all these points, but I just want to thank John and Ross for their continued support on everything we do with Yocto in the automotive team. So, Arm Automotive Solutions. So as other talks have already mentioned, software in cars is becoming more and more complicated every year. But interesting, the number of processing elements is decreasing. Also, the performance requirements are increasing due to ADAS, so advanced driver assistance systems. Therefore, Arm's vision for the future of cars is this idea of data center on wheels, and by that we mean it's high performance compute cores, largely borrowed from server IP, which we combine with real-time safety features and also a secure root of trust. So it's the best of both worlds. You have safety and performance all in the one SoC. And Arm Automotive Solutions is the reference stack that we use to demonstrate various automotive use cases on Arm IP. It's all open source, and I'll post the links at the end of the presentation. I think on the right, there's this is a BMW Series 7, and you can see we've got like an infotainment dashboard and the central braking system, and the idea is that potentially in the future, these could run on the same processing element with sufficient freedom from interference. We're not there yet, but that's the sort of ideas that we're talking about here. And so RD1A is the BSP that is contained in Arm Automotive Solutions, and it's an example architecture for automotive systems. So I'll go through these blocks one by one. There's the primary compute, which is a high performance compute system. It runs Linux or Zen. And it is augmented with what we call AE features, such as fault reporting. The AE is an ARM suffix that's applied to various pieces of IP, and it stands for Automotive Enhanced. Then next to it, we have the Safety Island, which is a real-time coprocessor, which augments the primary compute with safety features. In our stack, we run the Zephyr RTOS on this processing element. We also have the SCP, which is an M-class core, which is primarily dedicated to power control. And then we have the RSE, which stands for the Runtime Security Engine, which is the root of trust for the whole system. It bootstraps the system and also provides some runtime services as well. So all of this is integrated on an FVP, which stands for Fixed Virtual Platform. It uses Arm's modeling technology to demonstrate all of this IP in a tarball that you can freely download from the Arm website. And the FVP is also integrated into our stack. There's a recipe that downloads the binary, as you'll see later. So that's enough about Arm Automotive Solutions. In this presentation, I'm going to talk about various aspects of the Yocto integration. I've included some stats here. So we have 11 dependent Yocto layers, a lot of build jobs, a lot of recipes and BB appends, and we build a lot of packages. It's quite a big integration. I wonder if it's one of the bigger ones out there. I'd love to hear from other people who are sort of also integrating Yocto at this scale. I'd also like to highlight our documentation. We've got almost 40,000 words. It's quite extensive, and it documents all of the use cases I've just described in some detail. And finally, on this slide and many of the subsequent slides, I've included a click here element. So when you download the slides later, you can click through to the relevant part of the documentation or the code. So in this presentation, there isn't time to go into all the features of the stack, so I've chosen to focus on 4 aspects of the integration that I think are novel and interesting. If you're more interested in the automotive use cases, then I'll refer you to the documentation. But in this talk, I'm going to first of all talk about the CAS menu, which is a feature of CAS that I don't think gets enough attention. Then I'll talk about, I think it's the Zephyr integration. So we use Zephyr to integrate the applications that run on the safety island, as I mentioned earlier. And then I'll talk about how we use the open embedded quality assurance framework. We have quite a lot of test cases that are all integrated using Yocto and OEQA. And finally, I'll talk about GenImage, which is a tool we've started using quite recently to automate to generate our firmware images. So as you can see earlier, we have quite a lot of different processing elements, and the requirements the requirements to generate the flash images for this firmware are quite complicated, and GenImage has proved to be quite a good solution for us for that. So kicking off, CAS. I've had lots of talks at this summit about CAS, so I won't spend too much time talking about the basics. But it is essentially a package manager for Yocto. At least that's how I like to think about it. This is an excerpt from one of our CAS files. It downloads a layer called eWall, which provides our Yocto distribution, defines a local Yocto layer, and also adds meta-arm as a dependency, which contains all the recipes for most of the ARM firmware components. We also use CAS on CI to validate all our use cases automatically. So CAS menu is a feature of CAS that is a useful tool that you can use to simplify CAS configuration for end users. It's ideal for a reference stack such as ours, because it presents all of our features in a user-friendly format. And you can see here all of the use cases that you can build, which are presented as different build options. There's also an option at the bottom called Run Automated Validation, which just turns on Test Image Auto. So from one menu, the end user can build and test any of our features. It uses the kconfig format, which I think originated in the kernel. And on the left is an excerpt from our kconfig file, and you can see how that transfers across to the menu in the screenshots. So next I'm going to talk about Zephyr. So I did a previous talk about our work on Zephyr at the OE workshop in 2023. I've included a link to that presentation here. But the summary is that this is a layer that allows you to integrate Zephyr applications into your stack using Yocto. The main point from that presentation is it doesn't use West because it conflicts with a lot of Yocto's ideas about packaging and fetching dependencies. It uses CMake directly, which provides quite a nice integration. So this is the recipe here for what we call the critical application monitoring application, which lives in a separate repository. And this is to demonstrate how simple it is to build a Zephyr app using Yocto. You include this Zephyr sample.inc, or I think you can also use Zephyr image.inc now. you append your module, so your repository to the screw URI, and then set the Zephyr screw diet to the path of your application. So in only a few lines in a bitbake recipe, you can build any Zephyr application in a similar way. We also support out-of-tree modules, so the exact details are kind of out of scope for this talk, but Zephyr has a module structure which allows you to define boards and SOCs, drivers, subsystems, and have them auto-register themselves with the application. And you can register a custom module by appending to the Zephyr modules variable. In this repository, we actually have an in-tree module. So the source code for the module lives in the same repository as the Yocto layer that integrates it. And we use a little trick using file checksums to add that module to the application. And I had to look this up today, but the true here is whether the path exists at build time. And I think that affects caching when you build this recipe. The next topic on the menu is OEQA. So OEQA, as I mentioned earlier, stands for the Open Embedded Quality Assurance Framework. We use this extensively in our stack to validate our use cases. And this diagram kind of shows the basic structure of our test framework. So we have test cases which mainly live in the meta-arm auto solutions layer in Arm Automotive Solutions. Then that depends on a custom test target class, which lives in meta-arm, which sort of allows us to run test cases against Arm modeling technology. And that in turn depends on the OEQA framework in OEQA, which in turn depends on Python's unit test framework. So we're building on top of a lot of others' work here, but this has been very successful for us. We like writing tests in Python, and we've written a lot of them. I think all of our use cases have an associated test case, which is included in the open source reference stack. It's not perfect, so there's a test decorator called OE test depends, which we still use extensively, and we're sort of getting towards a place where all of our tests have to run in a very specific order. And we use OE test depends to create that ordering, which isn't ideal, but it is sort of a necessity because different tests run at different times during the boot flow of the system. Yeah, we're currently looking at alternatives to this that also that integrate with Yocto in a similar way, but so watch this space for sort of Arm Automotive Solutions 2.0. This is an example test case which validates the secure firmware use case. So the key features here are these test methods on the target, which are implemented in meta-arm on the custom test class. So we have a transition method which we use to put the model into a specific state. This is an idea that I slightly crudely borrowed from the LabGrid framework, which is another test framework that's available. And then we have sort of expect and send line, which are fairly standard wrappers around pexpect. The other notable feature here is that it supports multiple serial targets. It's not evident here, but the first argument to this method is the name of a serial target, which is important in other test cases. For example, we have a test case which tests the interprocessor communication. between the safety island and the primary compute, and that uses this argument to sort of use iperf between the two processing elements to validate the comms. And finally, I'm going to talk about GenImage. A bit of background on this. So, as I mentioned earlier, the RD1A firmware is quite complicated. There are 5 different flash images that are built from 6 different firmware components, and all these different firmware components are assigned as well using the MC Boots image tool. So in Arm Auto Solutions 1.0, we had 1 image per flash image, but I find the image concept in Yocto is a little bit overloaded. It's the final build target that you build is like it's in core image minimal or core image Sato, but it also has your rootfs, and it also embodies other elements all in the same image concept. So actually, on recommendation from Ross, we switched to GenImage, which has been very successful for us. It's there's no affiliation, but it's comes from Pengatronics, and it's integrated in the Meta PTX Yocto layer. The Arm Automotive Solutions 1.1 is based on SCARTgap, so we depend on Meta PTX SCARTgap. I understand that as of Styhead, the GenImage package now lives in Meta OE, and that Pengatronics, I think, are working on upstreaming the BB class as well. And yeah, and I mean, we love to see something like this in OEQA one day. I think this is an area where maybe Yocto could use some better abstractions. And this is sort of recapping a bit, but so we have this is what it used to look like on the left. We had an RSC ROM image, an RSC flash image, and an AP flash image, each of which had its own individual WIC image, and then our top level image, which built the rootfs, depended on the individual, well, on the do image complete task of each of the flash images. This is a little bit messy because these images, the recipes on the far left, aren't really images. We have to jump through some hoops to sort of disable test image, for example, and disable rootfs generation in these image classes. And it's also it's a lot of files for for what they are. So on the right is an excerpt from what we now have in 1.1, which is a GenImage configuration file. I think you can see the full file and the recipe in the link at the bottom, but this is a much cleaner solution to our complicated firmware problem. And that is all I have. So this is some links. The top link is a link to the developer.arm.com, which is the top level documentation. We have the main documentation hosted on Read the Docs. This link here is a good place to start. It's our reproduce page, which has all of the instructions to download, build, and run all of our use cases. And the software is open source and lives on the Arm GitLab instance. That is all. Thank you for listening. And if I had the chance to present today, are there any questions?